All right, Calc 3, welcome in. It's Thursday, November 18th, and it's the end of week 14. Goodness. So today we're going to be finishing 14.6, the triple integrals, and then move on to 14.7, which is triple integrals, but with the spherical and cylindrical coordinates, right? So there's even more options, if you can believe it, for dv. Yeah, we know that dv can be unpacked in 6 different ways, just using dx, dy, and dz. But then there's also a couple other more choices when the geometry calls for it, right? So I'm going to do one homework problem here, and it's a problem that wants us to rewrite a certain triple integral in the 6 different ways. So let me zoom in on this. Okay. And this is what we're talking about here. They've given us this picture here. Let me back off a little. Like that. Yeah, problem number 36 right here, right? So we have this little visual thing going on here. And it looks like we have the surface z equals 9 minus x squared. We have the plane y equals x. We have first octant because it's x greater than or equal to x, y, and z greater than or equal to 0. And then they've given us this triple integral. So the integral from 0 to 3, of the integral from 0 to x, and then of the integral from 0 to 9 minus x squared. And they've given us dz, dy, dx. And the instructions up here say, the figure shows the region of integration for the given integral. Rewrite the integral as an equivalent iterated integral in the 5 other orders. And so this will be a nice recap problem from last video and sort of a put it all together, hopefully, video as well for this. And we'll finish off the triple integration. Now, there's a couple other applications in this section that I'm not covering. For instance, I'm not going to do center of mass and total mass for triple integration, which would be finding the mass and mass of these objects, sort of these sorts of shaped objects like that. So our exam and our problem from the exam is going to just be a plate, a lamina. And so the double integral version, not the triple integral version. So you can safely skip the application stuff with the triple integral. But you will be having to sort of set up triple integrals and maybe even have to write them in several different ways, right? And so this will be a good problem for that. If you haven't already, go ahead and start to draw this picture, if you will. You'll need some sense of what this looks like. And also notice that they've rotated the axes a bit, that the x axis is going all the way here to the left and the y axis is like coming out towards you in the screen almost, right? And so that's a rotation than what we're used to seeing, where the x goes out this way and y goes out that way. So anyway, this is slight rotation, but the orientation is correct, right? But it is rotated from what we're used to seeing. Okay. All right. Once you have that jotted down, let's go ahead and see what we can start to say about this. I am going to write down a certain thing here. And then I will be ready. Okay. Let's take a look here. All right. So we have what this is this is the top view, right? This is the top view. And this will be good. So let's do our first order. I'm going to keep dz first because I can use the projection when you do z first, right? You project into the xy plane. And so that's what this solid looks like from top view. All right, and so the first order here is going to be triple integral of the integral of the integral. And I'm going to do dz first again, but now I want dx dy. So that'll be one of the 5 remaining orders, right? So dz has not changed. So this is still from 0 to 9 minus x squared. But now the dx and the dy have swapped, right? And so notice that this is, if it's a dy dx, back to our double integral idea, these are going to be vertical arrows starting at 0, going up to this curve like that, going up to this diagonal line. But dx, dy are horizontal arrows. So I'm going to start from this line, this diagonal line, go horizontally until I go up to this vertical line. And so that's going to be from starting at x equals what? Well, x equals y, right? Because that's the definition of this diagonal line, x equals y. And it goes until it hits x equals 3. From the picture, I can tell that's 1, 2, 3, and the vertical line there. Okay. And then the y, the arrows go from a height of 0 all the way up to a height of 3. And so there we have our first rearrangement. This is dz first, and then just dy dx swapped with dx dy. And there we have that. Okay. Now, the next one, I do have to change my first integral, right? So we either need to do dy or dx first. Okay. So let's see here. Let's do dy first. Okay. Now, dy, going back to our visual here, y is from left surface to the right surface. From the left surface to the right surface, right? And so what is the left surface? Now, remember, the left surface is actually behind this thing, right? Because we're usually, remember, this x-axis is usually pointing out towards you, right? So the thing on the left, that's this back wall, if you will, right? Back here, right? And so from visualization here, I could say that that left wall is y equals 0. All right, that's that back wall. That's what we would say the left wall if I was looking at it from the x-axis point of view. Right? Then arrows go through that and exit the right side, which would be this face right here. I'm highlighting it there. I'm sort of, there we go, right? Now that is the plane, that wall is the plane y equals x. So it looks like if I wanted to do a dy first, this is going to be y going from 0, the plane y equals 0, to the plane y equals x. And so I go ahead and jot that on paper. So this is going to be from 0 to x. Now I have to draw a picture of this 3D object projected into the xz plane, the other two variables here. So again, back to our picture. I want to look at what this looks like in the xz plane. And so I am going to draw a quick picture here and then show you what I get. What I see is definitely it's going to be this parabolic shape right here. Do you see that? That is what I'm going to see when I look at this from this angle, right? So when I look at it from this angle here, I'm not going to see that that plane is coming out towards me. I'm going to just see this outline of this upside down parabola, right? That's all I'm going to see. And so that means I am just going to see this upside down parabola z equals 9 minus x squared. So I'm just going to go ahead and jot that down. So I would just get something that looked like that, right? Now, of course, this is sort of reversed a little bit because remember, we always take our x-axis to the right and the z to the top. And remember, the picture I just showed you is rotated a little bit, right? But this would be its proper orientation if I was to rotate it back and put it flat on the table, right? That's what it would look like there, right? Now I can unpack this as either dx dz or dz dx. But this is the projection that I need to look at. And this is 9, z equals 9 minus x squared. Right, that's exactly what that is. Okay, so let's do this. So what I can do here is let's do dz dx. dz dx would be vertical arrows, like that, starting at z equals 0, going up to z equals 9 minus x squared. Okay. And then x goes from 0 sweeping through to 3. Okay. I can get my next order pretty, oops, don't do that yet. We can do dy, but now I'm going to do dx dz. So that's going to be the same picture, same projection, but now I'm going to think about horizontal arrows. These horizontal arrows start with this vertical line. This vertical line is x equals 0. And so this is going to still, this is y equals 0 to x, same first integration. But now dx dz is going to change these a little bit. So x starts at 0, and it goes to the right until it hits this. Now, that means I have to get x equals. Currently, I have z equals, right? So I do have to solve this for x. So subtract 9 from both sides, multiply by the negative, and then take the square root. So I get x is plus or minus the square root of 9 minus z. Now, since x is positive, this side is positive, I'll take the positive version. And so this is going to be 0 to the square root of 9 minus z. Then, where do the arrows go? They start at a height of 0, and they get pushed up to a height all the way up to 9. So 0 to 9. If I had my choice, that would not be a nice way to integrate. That square root scares me if I had to actually integrate that, yeah? But nonetheless, that is the setup. So we have our two dz first setups, then we have our two dy setups. And so now all I have left is my dx first setups. So let's go ahead and try that. So I'm going to do dx and then figure out whether I want to do dy dz or dz dy, right? But let's handle dx first. Now that's going to go, looking at our page again, this is going to go from back surface to the front, back to the front. So arrows are going to enter from the back and then go out the front, right? And it's x equals, yeah? So x equals, it's going to start at the plane, which is y equals x, and they go out the front. Now the front is this upside down parabolic cylinder, z equals 9 minus x squared. So it goes in the y equals x plane, and it goes out this front surface here, right? So that's how arrows enter and go out. So now I just have to make that in terms of x. So it's going to be starting from x equals y, that's the plane, to x equals with this equation, which we just did. We just solved this equation for x. And so let's go back here to paper. So I'm going to say that this is going to go from y, x equals y, to x equals the square root of 9 minus z, right? Now, I need to draw a picture of what this looks like in the yz plane. What would this look like if I had to draw this in the yz plane? Well, I'm going to see this widest part, right? I'm going to see this widest part. Now, what is that widest part? That's when this surface, the 9 minus x squared, intersects with the surface y equals x. That produces the widest part, and that's what I would see when I looked from this way, projecting onto the yz plane right here. All right? So projecting this on and seeing what that would look like, I would see that it's a parabola, right? And that x equals y would produce the largest sort of width of that, yeah? And so what I can say is to get that intersection would be this surface intersecting with this surface. In other words, this would just be z equals 9 minus y squared. And that would be what this looks like in the yz plane if I was to project that, right? Remember, projection's like a shadow, right? It doesn't actually have to be there, right? Like this surface does not have anything in the xy plane except this like little line, right? Like that, right? But remember, it's like a shadow being cast. So if I was to look at it from the left here, I would see that this is just a parabola in the yz plane. That's what it would look like. So that's pretty much the trickiest one we got there. So here's my picture of that. This is the y-axis. This is the z-axis. Here's 9. 1, 2, 3. And it's the same shape, but this is actually z equals 9 minus y squared, because it's the intersection of this surface with the plane y equals x. Okay, now that I have that, I can now make my decisions here. I can do dz dy. Z starts at z equals 0 and goes up until it hits z equals 9 minus y squared. And then y gets swept from 0 to 3. Okay. So that's my order there. One more order left. That's it. dx first, but now it's going to be dy dz. So x still goes from y to square root of 9 minus z. Now dy dz is going to be horizontal arrows on this. So horizontal arrows start at the line, that's y equals 0, to y equals whatever this is. Well, that's going to be this solved for y, which is going to be the square root of 9 minus y. Then z runs from 0 to 9. And there we have our 6 orders right there. Right? So this is those types of problems that, it's got a lot of detail to it, right? But I hope that you see each piece. I'm a little afraid to ask, but are there any questions with this one? Any questions with at least the general strategy? Or are there any specific questions about how I got some of these? Okay, I think chat has been stunned silent. They're silent and they're stunned. Okay. So I'm going to move on to 14.7, which is more triple integration, but now we want to work in different coordinate systems because sometimes the three-dimensional region of integration that we're working with, well, is much better described using cylindrical coordinates in some cases and spherical coordinates in others. So let's go ahead and take a look at 14.7. Let's see here. All right, first things first, we want to take a look at and remind ourselves of the coordinate conversion equations, right? So remember cylindrical. In fact, by the way, we've already done a cylindrical problem because the other day when I converted to polar halfway through the problem, that is cylindrical. And you might remember that because cylindrical is this hybrid coordinate system, right? The x and the y in this case are polar coordinates using r and theta, and the z is z, right? And so there's one rectangular coordinate, and then the other two are replaced with their polar version, right? And altogether we call that cylindrical. So now, if I want to form a triple integral, look what this is. I can see this sort of the way that I can sweep through this. Instead of thinking, bottom surface to top surface, or left surface to right, or front to back, or back to front, right? I want to think of it this way. There's some cool pictures here. I think this really does a nice job of visualizing how we sweep through this. Instead of from bottom up, or left to right, or back to front, check this out. We first integrate with respect to r, which means we radiate out from the center. So we do this radial thing out, right? Then we integrate with respect to theta. That's going to rotate this thing so it fills out that bottom portion, right? Then we're going to integrate with respect to z, and that's going to stack these little plates together and generate the entire solid. Do you see that? So that's how you basically go through with a cylindrical coordinate idea. You're going to radial out from the origin out to this. Then you're going to rotate a certain theta, and that in this case fills out that base like that. And then z moves that through the different heights, right? And so it fills out that entire space, that entire 3D surface. Yeah. So bottom line, though, all we have to remember is that when we change to cylindrical, like this formula suggests, this formula looks really complicated, but all it's saying is if you have a triple integral in terms of x, y, and z, dv, it can be unpacked as x equals r cosine theta, r equals sine theta, and z. And remember, the polar gives you an r. So now dv can be unpacked as r dz dr d theta, right? So dv has now another option, if you will, right? And the same rules apply here. These limits, this first limits here, can be in terms of two variables, the r and the theta. These can be in terms of one, which is just theta. And then these are just going to be quantities, numbers, right? And so let's go ahead and just do our first example. All right, let's see here. Oh, once again, their first example's always like weird. They have like they pick the weirdest integration problems. Let me see the old book. Let me see if there's one that's a little nicer and gentler for our first example here. Yeah, here we go. Okay. So for our first example, let's try this. We have a solid T, and it's bounded by a cone. Bounded by a cone given to me as z equals the square root of x squared plus y squared. Okay. And the plane z equals 2. Okay. All right. Using a triple integral, let's find the volume. Let's find the volume of this thing. Okay. Okay. All right, so here we go. We first want to get a sense of what this looks like. This is a cone, and if you notice that if I square both sides here, you get circles. If I was to cut this into any horizontal place, it would look like a circle, right? And the radius of that circle depends on the height of where you're at. I mean, if I'm in the XY plane, well, the only thing that I have in the XY plane is if z is 0, right? And so the only point that would be is the origin, right? So this starts with just being a dot, right? So if I do this, right, it starts being a dot right there, and I just get bigger and bigger and bigger radii circles, right? So I get this cone shape. And I can do something like this. Okay, something like that, right? Notice that every time I chop this horizontally, I get a larger and larger circle, right? And we can actually say that this is the top of it. This is actually the top of the thing, and we'll call that z equals 2, right? That's what that is. That's a horizontal plane, right? So this is just a cone. Starts off at the vertex there, at the origin, and it goes and it has a flat top like that. Okay. All right. So I want to set up a triple integral that finds the volume of this. Now, don't get me wrong. You might know what the volume of a cone is, and you can, of course, use that formula if you need this in a practical way, but we're trying to introduce, triple integration here. So let's see if I can get at it this way. The volume of this thing is going to be the triple integral over t dv. And if I was to just triple integrate over the surface 1, right? Remember, this is a 4-dimensional surface 1. dv there, right? That should get me the volume, right? But now I am going to want to use maybe cylindrical coordinates here, right? Because I know if I'm going to integrate with respect to z first, I have to project this downward into the xy plane. And looking at this from above, all I'm going to see is that widest circle, right? Looking from above, looking down, right? I'm only going to see this circle, yeah? So when I project this down, that's all I'm going to see as a shadow in the xy plane, right? That means I'm going to expect the need to use maybe polar in the xy plane. So it looks like cylindrical would be a great coordinate system here to use. So let's go ahead and do that. What I'm going to say here is that this is going to be the integral of the integral of the integral. We replace dv with what it's equal to, which is r dz dr d theta, right? Okay. Now, since this first one is rectangular, okay, this first one is rectangular, we are going to think from bottom surface to top surface, right? That's how dz first works, right? So what is the bottom surface for any arrows that go through this shape, right? If I do an arrow that goes vertically, it's going to enter on the cone and then go straight up until it hits the flat top, right? Any vertical arrow will do that, yeah? Okay, so we're going to go from the bottom, which is the cone, up to the flat top. In other words, from z equals square root of x squared plus y squared, okay, to z equals 2. Now, this would be fine if this was rectangular, but x's and y's are not allowed in rectangular, right? So, but thankfully, x squared plus y squared is equal to r squared. So I can rethink of that, and look at that. Square root of r squared is just r. So this means that z starts at r and goes to 2. Goes to r to 2. See that? So that bottom surface in cylindrical is just described as z equals r, right? And so that makes this integration really easy. No more square root. That's beautiful. It's wonderful, right? Now, project this down into the xy plane. So here comes my second picture, right? Here's my second picture. Here's the x-axis. There's the y-axis. And because of this, I know that z equals 2. That is going to be the circle that I see, right? That is going to be the circle that I see, right? And so I'm going to see that's the intersection of z equals 2 with the cone z equals square root of x squared plus y squared. That's what I'm going to see. I'm going to see that widest part, and that is the intersection of those two surfaces, right? So I am going to now plug in z equals 2 into this surface, because that would mean it's the intersection of those two. So I'm going to get 2 equals square root of x squared plus y squared, right? Which I can then reinterpret, right, as x squared plus y squared equals 4, or otherwise known as r squared equals 4, or r equals 2, right? This is a circle of radius 2 in the xy plane. See that? So now, to continue on with this, what does r start from and end at? Well, it starts at the origin, starts at r equals 0, and radiates out until it hits always r equals 2. There's going to be 0 to 2. And then theta starts at angle 0 and rotates all the way around to get to 2 pi. There's the setup. That triple integral will give us the volume of that cone. Okay? That gets us the setup for that. Let's go ahead and actually do that example. Let's actually calculate that. And then maybe you could even check it with a known formula for the volume of a cone. Yeah? So let's go to it. I'm going to do integration with respect to z first. So the integral of r with respect to z, well, that's going to be r times z. Evaluated from r to 2, dr d theta. That's going to be the integral from 0 to 2 pi of the integral from 0 to 2. You're plugging in these values for z. So I'm going to get 2r minus, plug in r squared, dr d theta. All right, let's go ahead and continue on. Now I'm integrating with respect to r. So I'm going to get 0 to 2 pi. Antiderivative of 2r is r squared, right? Divide by 2 and the 2's cancel. Minus r cubed over 3, evaluated from 0 to 2, d theta. I'm going to get the integral from 0 to 2 of, plug in the 2, which is 4. 4 minus 8 thirds, minus a 0, minus a 0. Good stuff. D theta. That's going to be a constant. In fact, 4 is what? 12 thirds. And so 12 minus 8 is 4 thirds. So this is going to end up being 4 thirds times the integral of 0 to 2 pi of d theta. And this is just the length of the interval. And so this ends up being 4 thirds times 2 pi, which gets me 8 pi over 3. Which I hope matches the volume formula for a cone. That would be really embarrassing if it didn't, right? But you should be able to look up or Google a formula for the volume of a cone and be able to get that. All right. Any questions with that? Any questions with that? Okay, if we're doing good in chat, let me know. Again, I think chat has been stunned silent. A little stunned silent, okay. All good. For those of you who say a little, do you have a specific question, or is it just sort of like, whoa, what's going on? Right. Yeah, unfortunately, before we do this sort of thing, it is just a lot, isn't it? Yeah, it is a lot. Mm-hmm. Yep, just getting used to just how much it is, right? Yeah, I agree with that. All right, let's go ahead and do another example using cylindrical. Let's do another example here. Okay, I found another example here we can try. See what we make of this. They say evaluate the triple integral over t of x dv, where t is the part of the solid in the first octant bounded by the paraboloid z equals x squared plus y squared. Okay? So this is not a cone. This is more of a parabolic bowl. So it's not as extreme as the cone. It's not like a V shape here like this. It's more curved. It's a parabolic bowl. Everywhere you look at it, it has a parabolic shape, right? And the plane z equals 4. Okay. So we want to get some sense of what this looks like, right? So you can either use GeoGebra or think of it again as parabolas, right? Like if you think of y being 0, this looks like z equals x squared. So that's a parabola. But then if you make x 0, it looks like z equals y squared, right? And so it looks like a parabola this way, and it looks like a parabola this way. And so it's actually just a parabolic bowl. So let's just get a rough picture of that so we can say that we have one. All right, so I'm going to do something like this and like that. And it's going to look like a circular top still, isn't it? Right? Because this is still x squared plus y squared equals a number. And so that is going to represent a circular thing, right? A circular object when I cut it that way. Okay? And in fact, the top of this is going to be the plane z equals 4. Okay? All right, so that's the shape that we're working with. Okay. So now you make a choice, right? It's like, well, do I want to use rectangular coordinates? I mean, they want me to evaluate x, but that's no big deal. I mean, I can still switch this to cylindrical, right? And what would be good to use cylindrical? Well, look for things that you can do from bottom surface to top surface pretty easily, right? Like for here, instance here, z starts at the parabolic bowl. Arrows go vertically, starting at the parabolic bowl, and go up until it hits the flat top. And I have a good description of the parabolic bowl in terms of z, and I have a good description of the top in terms of z. So it looks like dz should be first, and when I project this into the xy plane, I'm going to get something that's going to be easily described with cylindrical coordinates. So yes, this is a cylindrical coordinates problem, right? And I'm speaking like in general when you have like choices, when it says, hey, just evaluate this, and you have to make the call whether you are going to use rectangular coordinates or cylindrical coordinates, right? And so you got to make that call. Here, I think it's a pretty easy call to say, yeah, I think cylindrical is going to be a good thing here because I'm seeing x squared plus y squared, which is usually a good sign. And I'm seeing easy z values, so that's a good sign. Yep, this is cylindrical. Let's go ahead and pursue that plan. Cylindrical coordinates, okay? So I want to evaluate the integral of the integral of the integral of x. But remember, x is not allowed in cylindrical. X is r cosine theta in the cylindrical world. So I replace x with what it's equal to. Then I replace dv with r, dz, dr, d theta. Yeah. Okay. Let's now figure out z goes from what to what. Well, it starts at the bowl and goes up to the top, up to the plane surface. So I know it definitely hits z equals 4. And it certainly starts at z equals x squared plus y squared, which in cylindrical is just r squared. So z goes from r squared to z. Now I just need a picture in the xy plane. All right, I'm going to project this down. So this is going to be the widest part. The widest part is when this bowl intersects z equals 4. In other words, I need to look at 4 equals x squared plus y squared. Now that is a circle of radius 2, right? Do you see that? Because it's x squared plus y squared equals 4, which means that this is 4 equals r squared, which means r is 2. So this looks like a circle of radius 2 in the xy plane. This is the top view of that parabolic bowl. Now I can just say r goes from 0, radiates out to 2. And then theta goes from 0 to 2 pi. Okay. All right. So there we have the setup. Are there any questions with the setup? Any questions with that setup? I'm not anticipating any. Oh, I've made a typo. There should be questions with this setup. I've made not a typo, but I just wrote down a mistake. Does anyone see my mistake? Take a look at those z limits again. How could I integrate with respect to z when I'm going from z equals r squared to z equals z? That doesn't make any sense. What should this be? It goes from the bottom up to the top. And what is the top? Z equals 4. Yep, I made a mistake. Go ahead and please correct that. I wonder if I said the right thing, but just wrote the wrong thing. Okay. Probably people in the video watching this earlier was like screaming at me through YouTube. Like, what? Okay. All right. With that correction, does that make sense? I think that makes sense now. Okay. All right. So let's go ahead and actually do this integral. I am going to simplify before taking the integral. So I get r times r, so that's going to be r squared cosine theta. Integral with respect to z, then r, then theta. Okay, here we go. These are along for the ride for now. I'm integrating with respect to z first. This is all constant relative to z. So I'm just going to have z r squared cosine theta evaluated from r squared to 4. Okay. You have the integral from 0 to 2 pi of the integral from 0 to 2, and you're plugging in for z values. So you're going to get 4 r squared cosine theta minus r squared times r squared. So that's r to the 4 cosine theta. Dr d theta. Okay. Now this looks really nasty, right? This looks really bad. But remember, I am integrating with respect to a single variable r. And so cosine is treated like a constant. So I'm not actually integrating these trig functions yet, right? I'm still just integrating r. And r is just r squared and r to the 4. So even though it looks really nasty, it's not actually too bad, right? So the integral from 0 to 2 pi of, let's go ahead and do this antiderivative. We're going to say r cubed. The 4 is still out in front, divide by 3 times cosine of theta minus r to the 5th, divide by 5 cosine of theta d theta. Oh, evaluated from 0 to 2. D theta. And now I'm plugging in for r, right? So the 2 gets plugged into here. I'm going to get 8. 8 times 4 is 32. This is going to be 32 thirds cosine theta minus, plug in the 2 here. This is also going to be, 32 as well, right? 2 to the 5th. Yeah, 2 to the 5th is 32 over 5. Cosine of theta, d theta. Okay. So that's how many cosines I have. So I have 32 thirds minus 32 fifths for a fraction of 64 fifteenths. Ugh, but okay. All right, I guess. So this is going to be the integral from 0 to 2 pi of 64 fifteenths cosine of theta d theta. That's a constant that'll get pulled out in front, and now I am just integrating cosine. So at each individual step, it wasn't terrible, right? It wasn't really terrible. So wait a minute now. Cosine, the antiderivative of cosine is positive sine. Oh, are you kidding me? I plug in 2 pi, which gets me 0, and I plug in 0, which gets me 0. After all is said and done, I got 0. Now, don't freak out on me that I got 0. It's possible to get 0. Remember, I'm not calculating the volume here. They had me evaluate the triple integral of x dv, right? Which is not the volume. So they're basically saying, travel through this entire shape, right? And think about your x coordinate as you go, right? And in some sense, what this is saying is that there's a certain amount of x coordinates that are positive and a certain number of x coordinates that are negative, and that whole sort of thing net balances out to 0. That's what basically that's saying. But I know that's rather undramatic to get 0 at the end of that problem like that. So, all right. Any questions with that? Any questions with that? All right, great. We're now ready to start with spherical coordinates. So let's take a look at this picture. All right, so spherical coordinates, you might remember, are these three coordinate equations, right? We get x equals rho sine phi cosine theta, y equals rho sine phi sine theta, z equals rho cosine phi, right? And so you can have the spherical block. And actually converting this to a triple integral, the dv actually unpacks rather complicatedly. There's a little extra baggage here. You know how the polar starts with r dr d theta and the little r comes out? That r comes out because of the formula to find the area of a polar region. So that extra r came out in that derivation. Well, as you can imagine, finding the volume of this spherical block actually involves a little bit like this. And it says it can be approximated by this little thing in front. And the extra baggage, if you will, the extra thing that comes out instead of the r, spherical, it comes out as rho squared sine phi. And that is simply because that comes out when you're trying to find the volume of this spherical block, right? So I'm not going to pay too much attention to that, but that is sort of the price you pay to convert to spherical. You're trying to do a rectangular integral, right? But you're forcing it into a spherical coordinate system. And sometimes they don't play very nice with one another. And so that extra little term comes out because of the way that we calculate volumes, right? So anyway, we have that extra little thing there. So let's recap what dv unpacks as, right? So we have that dv can unpack as, of course, the 6 rectangular, right? So we have dv can certainly be dz, dy, dx, and the 6 others, or 5 others, right? We also have r dz, dr, d theta. That can be an option. And now we have a third option with spherical coordinates. That's going to be rho squared sine phi, d rho, d phi, d theta. And so that is how dv gets unpacked in the spherical world. Now, this is going to be great when working with spheres and like certain spherical topped cones. And there's all sorts of applications for this, all based on the geometry that you're working with, right? So let's go ahead and again, wanted to point your attention to these pictures here. So here we have a cone, and unlike the other section, the other problem that we had, this cone has a spherical cap. See that? It's not a flat top in this picture, right? This is going to be great for spherical coordinates because if you remember, rho is always a distance from the origin out to, radiating out from the center, right? And notice that if you were sitting down here in the corner like this, in this point, and you looked around, you would always have a straight line look from 0, and it would actually look outside or onto the sphere, right? And you could only look as this low, right? You can't like rotate all the way down here, right? So you're sort of like stuck looking from, like this way or this way. The tip of this is always on the spherical cap, right? And that's what I mean by radiating out from a center, right? No matter where you look within the bounds of that cone, you're going to always be going straight from the 0 out through the spherical top. This is going to be a great way to think about spherical coordinates. So let's see this again. So you think about going from 0, going out until you hit the spherical top. Then you vary phi, which means it's going to now rotate this way. Remember, phi is the angle you make from the positive z-axis. So it starts to fill out this wedge shape right here. Then you do theta to spin that wedge all the way around, generating the entire solid. Do you see that? That is yet another way to traverse this entire solid. How do I get to every point in the solid? Well, you can always think of it as going out a certain distance from the center. You can then rotate down a certain phi, and then you can rotate that around and literally get to any point inside of the solid that you want. That's the visualization of spherical coordinates, how I can fill in that shape, right? Now, let's go ahead and see if we can set up problems like this and work with our first, maybe our first problem like that. So here we go. So they're asking us to find the volume of Q, which is bounded below by z squared equals x squared plus y squared. Okay. And above by x squared plus y squared plus z squared equals 9. That's a sphere. That might be your sign that you should use spherical coordinates, right? So let's see here. We want to find the volume. So I know what the triple integral is that I need to do. The volume is going to be the triple integral over Q dv. Right? That is the setup. Right? Volume is going to be integrating over the surface 1 to get me the volume, like that. So now I have to set up my limits. And we know it's going to be spherical. Well, 1, because it's in the spherical section. And 2, probably because there's a sphere involved. And so that might be really nice to work with spherical, because right away I know that x squared plus y squared plus z squared is rho squared. And that means that the sphere is rho equals 3. All right, which is really nice to work with. Okay. All right, so let's get started. I'm going to unpack this. dv in spherical becomes rho squared sine phi. Then d rho, d phi, d theta. Okay. Okay. Now, to get a sense of this, by the way, this is a cone. This is z squared equals x squared plus y squared. So this is exactly like what we did earlier when it was z equals the square root of this. And remember, that was a cone. So we end up with a picture that looks like this. We get this cone, but instead of a flat top here, instead of this flat top like this, we actually get a spherical cap. So this cone is going to go forever, and then there's this sphere that intersects it, right? And so I'm not going to draw that part of the sphere, but it's going to intersect somewhere, come to here, and then make like a little cap, if you will. Like something like that. It looks like a snow cone, right? It looks like a little snow cone, right? So I'm finding the volume of a snow cone. That sounds lovely. Okay, so this is the sphere, rho equals 3. And this is, well, let's see if we can get this in terms of spherical, right? Because right now it's z squared equals x squared plus y squared, and none of that is allowed in spherical, right? So let's get to maybe working with this and getting it to look like something like that, yeah? Okay. First things first, let's see here. I want to be careful with the order that I do things. So now I'm second guessing how I want to do this first. Let's do this, okay? Let's think about rho. I'm going to set up the limits for rho first. Now think of arrows going from the origin, always radiating out from the center, and where do they always go out of? And you see that it's always the surface of the sphere. So that no matter where I'm looking from the center, they're going to radiate outwards and exit the spherical cap. So that's really easy to describe in spherical. That means I start with a distance of 0, starting at the origin, and it always exits at rho equals 3. Right? Okay. So that's actually pretty nice. That's cool. Okay. Now, secondly, I now need to come up with phi. Okay? Phi, remember, is the angle that this cone makes, right, like that, is the angle that it makes with the z-axis. So I'm looking for this angle here. Now that's going to come into play when I start to think about how this cone intersects with this sphere. That's what makes that angle, right? It's where that spherical top intersects with that cone. And it makes that angle like that right there. So intersect the cone with the sphere. Okay? Because that's going to give me information about how far over this is bent. Like, so for instance, is this cone really narrow like this, or is it really squat like this, right? What is that angle that it makes? And this is a way that's going to help me get that, because it's exactly the angle that meets up with the sphere that intersects with it. Okay, so now what does that mean? That means I can actually replace x squared plus y squared in this formula with what it's equal to, which is z squared. So I'm going to say x squared plus y squared plus z squared equals 9. And I'm going to replace this x squared plus y squared with what the cone says it is, which gets me 2z squared equals 9. Z squared equals 9 halves, which gets me a z of 3 over root 2. Now that feels like it didn't help. I got a z value out of it. I really want a phi value, right? I want the angle, not z. But here's where we remember the formula. Here's where we remember the formula for z. Check this out. Z equals rho cosine phi. Rho cosine phi. See that right there? And so I'm going to use that formula. Now that I know what z is, it's 3 over root 2, I will then replace that with phi and get a rho with, and then get phi from it. I'm going to get the angle this way. So let's do that. Okay. So z equals rho, oops, go back to here, cosine phi. Okay. That means that cosine phi is z over rho. Z is 3 root over root 2. All right. Rho, what is rho when I'm here at this point right there? That's rho equals 3, right? Because it's on the sphere. which means it has to be that the case that phi is 3. So phi is 3. And that has to equal cosine of phi. But look, the 3's cancel, and I get 1 over root 2 cosine of phi. And taking the arc cosine implies that phi is pi over 4. This makes a 45-degree angle, this cone. This cone makes a 45-degree angle with vertical. And that is the value I needed. And I was able to get that by simply, I shouldn't say simply, because I don't think it was simple, but recognizing that it was the intersection here of the cap, the spherical cap, with the cone, and playing around with that intersection, getting specific values, and then using my formula to get what phi has to be there. So I am, bottom line, integrating from something pretty simple. I'm integrating from angle 0 and then rotating down to pi over 4. So 0 to pi over 4. That took a lot of work to just realize that this limit is going to be easy. It's 0 to pi over 4. Then theta. How do I take this whole thing and spin it around? Yes, I want the entire cone. So I just want to take that like a wedge thing and then just rotate it around, creating the entire shape. So that's going to be 0 to 2 pi. That's the setup of the volume of the snow cone. See that? And let's go ahead and do that integral, because that integral is not going to be too bad. I know this looks really scary, but again, remember we're integrating with respect to single variables along the way. So all the other stuff gets to be treated like as constants. Yeah. So this actually isn't as terrible as it might look in that way. All right. Any questions before I move on to actually calculating this? Any questions with the setup here? By the way, this one is in your textbook. This is the one that's in your textbook. This is example 4 on page 1028. Example 4, page 1028. So if you want to take a look at their pictures and their description. Okay. All right, let's go ahead and now calculate this triple integral. So we get 0 to 2 pi of the integral of 0 to pi over 4. Okay. And I'm integrating with respect to rho. So it's going to be rho cubed over 3 sine of phi, evaluated from 0 to 3. d phi, d theta. All right. Plug in 3. Plug in 3. 3 cubed divided by 3 is 3 squared. 3 squared is 9. So 9 sine phi. Minus plug in 0. Great. Wipes it out. Wonderful. d phi, d theta. Okay. Then, you can take the 9 out all the way. It's a constant relative to phi and to theta, so it can go out all the way if you want. And just hang out in the front. Now, what is the antiderivative of sine? Well, that's going to be negative cosine of phi, evaluated from 0 to pi over 4. So I'm going to get 9, integral from 0 to 2 pi. Plug in pi over 4, minus a minus cosine of 0, d theta. These should be easy, right? Let's see. The integral from 0 to 2 pi of cosine of pi over 4. Cosine of pi over 4 is root 2 over 2. So this is going to be negative root 2 over 2 plus cosine of 0. So cosine of 0 is 1. Okay. All right. Bottom line, look at this. This is a constant. Yeah, I mean, it's an ugly number. It's 1 minus the root 2 over 2. But this is a constant. It'll multiply with a 9, and then I get the length of that integral again. The integral from 0 to 2 pi of d theta just gets me a 2 pi. And so this is going to be 9 times 1 minus root 2 over 2, that constant comes out, and then times 2 pi. And let's see, maybe you push the 2 through to cancel that, and then multiply there, and then I get 9 pi 2 minus root 2. Sure, that looks clean. And there is your result. That's the volume of the snow cone. Now, you might think that that's difficult, like, wow, that was a difficult problem. And it is, it's challenging. It's using a coordinate system that we're not very used to. But I would not wish this problem on anyone having to stick with X, Y's, and Z's, right? Because there is going to be a point, if you stuck with X, Y's, and Z's, you are going to have to solve these for Z, X, or Y and get square roots of sums of things and sums of squares of two variables. And you're going to get bogged down and stuck really quickly if you're forced to stick with rectangular coordinates here. So even though spherical coordinates may not be very, you're not very comfortable with them, maybe you're not very adept with them yet, the price alone is worth it because I was able to integrate from constant to constant, constant to constant, which makes the integration a whole lot easier than having to deal with, embedded square roots of sums of things. All right. So yeah, definitely the only way to go here basically is spherical coordinates, right? With that. All right, everyone, that finishes 14.7, and that actually finishes chapter 14. So we are, maybe that's good news for those of you who aren't a fan of integration. That is the end of it. That is the end of new stuff as far as that goes. And so you'll want to be practicing double integration. You'll want to be practicing the applications of double integration. And then you want to practice now the new triple integration. So yeah, but for triple integration, basically just be able to change, sort of like the problem I did at the very beginning of today's video, and then be able to work with them in spherical and cylindrical coordinates, right? But yeah, so you should be able to practice with chapter 14. Now remember, for this class, we do not have a cumulative final, but our final exam is going to cover chapter 14 and what we cover in chapter 15. And so we will start chapter 15 next time. And remember, next week we only have one video because of Thanksgiving. And so, yeah, we only have 3 videos left, 3 classes left, 3 videos. And so we will get through chapter 15 in 3 days, right? Chapter 15 basically combines a lot of the things that we've been talking about and really puts a nice end to the semester. You've come a long way, folks. That's what we can say. We have come a long way with all of this, yeah? Christian, go ahead with your question. We have a question here. Is this good for everyone or just a personal question?
Yeah, it's good for everyone. So just, I might have been looking at it, dumb question. So on the last step of the last integral, did we just not, so because it was a constant, we just, okay.
So I'm using a shortcut that I like to use all the time. Let me do it out the regular way. I did get to something like this, right?
Right.
So this would be theta evaluated from 0 to 2 pi, which would be 2 pi minus 0, which is 2 pi. Right? So it's quote unquote easy, but I really love the shortcut of recognizing, oh, this integral is the length of the interval. So 0 to 2 pi. So so if I said, hey, what's the integral from 4 to 7 of dx? You can instantly say 3.
Right. Okay, that makes sense. It's just recognizing that pattern and
exactly right. Yep, exactly right. Yep. Thanks for that. Yeah, that's a great question. Okay, everyone. Well, with that being said, hope you all have a great weekend, and looking forward to checking in with you on Tuesday. And until next time, be well and take care of yourself, all right? Bye now.